In this problem, we have a solenoid, and you can kind of visualize this problem with this diagram. So it's an infinite solenoid, and you can imagine it curling around the z-axis. And this is a very bad drawing, but believe me, each one of these coils have a radius of a, and then we're told that there's a current I going around the solenoid. So from chapter 5, you know that inside the solenoid, there is also a magnetic field that is pointing upwards. And so as this current changes, so as this current varies, Faraday's law dictates that there is going to be electric field generated. So once again, let us remind ourselves what Faraday's law is. So the line integral along the electric field that's generated by this changing magnetic field is equal to the change in the magnetic flux. So in this case, first of all, we need to figure out what the generated electric field is pointing towards. So what is the direction of the generated electric field? And essentially, you can apply all the symmetry arguments you did in chapter 5 when you dealt with problems involving the Ampere's law. So here, so back then in chapter 5, if you have an electric current that's going upwards, this will generate a magnetic field that goes around. And this is essentially the same thing, only this time we've swapped the places. So instead of having a current that goes up and generating a magnetic field, we have a magnetic field going up, and because it's changing, it's going to generate an electric field that is going to be circular. And it's circle due to a symmetry argument. There is no preference for this electric field to kind of contort towards any direction, so it has to be symmetric, it has to be circular. So knowing this immediately, we can simplify this expression. So let us first consider the case when we're inside the solenoid. So what is the electric field generated inside the solenoid? So I can imagine a hoop being drawn here, this hypothetical hoop with a radius of r. So this has a radius of r. And so the line integral becomes the magnitude of the electric field, E times 2 pi r. And this is going to be the change in the flux. So what is the flux? So recall from chapter 5, you can use Ampere's law to derive this again, but the magnetic field inside of the solenoid is uniform, and it's equal to mu times n times I. And since we're calculating the flux, we also need to multiply it by the area. So the loop that we've just drawn, it encloses an area of pi r squared. So there we have it. So immediately you see the pi's, they cancel out, one of the r's, they cancel out. So you see that E is equal to negative mu n r divided by 2 di dt. So I is a function of t. So this is the only thing that is going to be affected by the derivative over here. And this negative sign is due to Lenz's law, so it dictates the direction where the electric field is moving, and you can determine the direction of the electric field using the right-hand rule. So just now we drew this circle over here, so I'm just going to pull this out. So when we considered this circle over here, we considered the flux coming out in the upward direction, upward to the z positive direction, to be positive. And using the right-hand rule, that means the electric field going in this direction is positive. So if di dt is increasing, so this is positive, this whole expression here would be negative, thanks to the negative sign at the front. So if di dt is increasing, the electric field will be going this way, because of the negative sign. If di dt is decreasing, if the current is decreasing, then this will be negative, and along with this negative, this whole thing will be positive. And then the electric field will be going in this direction, the so-called the positive direction. So this is how the negative sign works, in case you're wondering. So the second case we can consider is the outside case. What is the electric field generated outside of the solenoid? So we do the same thing as before. We draw this hypothetical hoop that goes around the solenoid, and we apply the same equation. We apply Faraday's law. So we evaluate the line integral E times 2 pi r. So the radius of this is equal to r, and the amount of flux that's going through this. So recall that there is no magnetic field outside of an infinite solenoid. So the only flux that's going through this circular hoop, I can draw it here. So this entire radius r. So the only flux that's going through is within the area covered by the solenoid, which has a radius of a. So the change in flux is equal to the magnetic field mu and I times the area pi a squared. So as opposed to the previous example, we use r squared. But because outside of the solenoid there is no magnetic field, so we use a squared this time. So we can cancel this out. So E is equal to negative mu and a squared divided by 2r di dt. And once again, the negative sign means the same thing as before, so you can figure it out yourself. So this is the answer.